Good morning. Today we will continue in our lecture series. This is the last lecture in our series, and today we will talk about Dirichlet processes. One way, Dirichlet processes are in some way similar to Gaussian processes. It is again a non-parametric model, and in the case of Gaussian processes, we extended we can understand Gaussian processes as an extension, infinite extension of multivariate normal distribution. Dirichlet processes can be understood as infinite extension of Dirichlet distribution. So let's talk more about Dirichlet processes.
Okay. Thank you. Okay, yeah, so first we'll start off introducing the Dirichlet distribution, and then we'll go to the Dirichlet process and extend it in that case. So let's start off with the Dirichlet distribution. Well, with the categorical and multinomial distribution. So consider we have a random variable x taking k possible outcomes. So for example, we're tossing a dice. X is the outcome of the dice, and we have 6 possible outcomes. So among n independent and identical trials, n tosses of our dice, we let nj be the counts of the jth outcome. So nj for j equal 1 would be the number of times we observe 1 when we roll our dice. And just note that the sample size is the sum of our counts by definition. So the distribution of xi is given by the categorical distribution. It's parameterized in terms of a vector p, p1 to pk, and these are positive and sum to 1, so they are probabilities. And the probability that x is equal to the jth outcome is just pj. Now we can, from the categorical distribution, we can derive the distribution on the counts. And the distribution on the counts is given by the multinomial distribution. So this is just pj to the power of the counts, nj, the number of times we've seen the jth outcome. And this is the multinomial coefficient here. So if we have n distinct outcomes, this just counts the number of ways I can throw n objects into k bins. An example is n1 to nk could be the frequency of words in a text. Yep. Okay, the Dirichlet distribution is the conjugate prior to the multinomial likelihood. So this just means if we look at the multinomial likelihood as a function of p, it's just proportional to this term here. So if we replace the sufficient statistics with some parameters, we get the Dirichlet distribution. Okay, the parameters of the Dirichlet distribution are a vector of alpha 1 to alpha k such that alpha j are all greater than or equal to 0. And we can reparameterize these parameters in terms of alpha, which is called the total mass or the precision parameter. So it's the sum of all of the alphas. And p naught, which is just alpha 1 divided by alpha. So the expected value of pj is just p0j, so we can interpret this parameter p0 as our prior guess. And if we look at the variability of pj, it's given by this formula here. So we can interpret alpha as our precision parameter. It controls the variability. So in particular, as alpha goes to infinity, we see that the variance goes to 0, and we converge to our prior guess. Okay, here's just some examples of Dirichlet densities taken from Wikipedia. We can see how different parameters control the mass. This is an example of a 3-dimensional vector here. So it lies on the k-1 simplex. So we have, it must lie in this space here. And here's examples of the density for different values of the parameters. Okay, connections with other distributions. If we define zj to be independent gamma oops, that's a little typo there. That should be alpha j. Independent gamma alpha j. And if I transform these z's appropriately here, then the distribution of this z under this transformation is equivalent to the Dirichlet distribution. So this property is often used to simulate from a Dirichlet distribution. We just take k independent draws from a gamma distribution, and we normalize appropriately to get the Dirichlet distribution draws. Another connection with another distribution, if I define Vj to be independent beta, where the parameters satisfy this condition here, for j equal 1 to k minus 1, and the last Vk is degenerate at 1, then I can transform these beta random variables, and their distribution under this transformation is equivalent to the Dirichlet distribution. So equivalently, I can say that Vj is equal to this transformation of p's. So if you're familiar with survival analysis, you'll recognize this as the hazard function. So this is the probability that I die at time j, given that I survived up to j. Just to note here, we could consider a more flexible parameterization here using alpha j and some general parameter here, beta j, and look at the induced distribution on our vector of probabilities. And this is known as the generalized Dirichlet distribution. This is also conjugate to the multinomial likelihood, but it's a more flexible parameterization. Of course, in this case, we lose some properties if we use the generalized Dirichlet distribution because we require an ordering of these random variables. Okay, symmetric Dirichlet distribution. That's just defined where my prior guess has equal mass for at each point. So here's some draws from a symmetric Dirichlet distribution with different values of alpha. So here's alpha equal to 0.1. We see that in this case, we tend to have high mass on one value and very small mass on the other values. Instead, as alpha gets larger, our mass tends to spread out even more, and if we look at, say, alpha equal to 100, we would get something very close to our prior guess of, here we have 10 points, so we would have, our prior guess would be 0.1 here. And that's because this alpha controls the variability. So we said before that as alpha goes to infinity, we get close to our prior guess. Oops. So we see here that the larger alpha is, the closer we are to the symmetric prior guess. And these samples were drawn based on this property here. Okay, so if we have the categorical likelihood, and we use a Dirichlet prior, this leads to a Dirichlet posterior. So we said the Dirichlet is the conjugate prior. This is easy to show, right? Oops. The posterior of P given X, this is just proportional to our prior on P and our likelihood. As a function of P, this is just proportional to the product from J equal 1 to K, Pj alpha j minus 1, and this is just proportional pj to the nj. So this just becomes product from j equal 1 to k. So these are our updated parameters here of the Dirichlet. Again, we can reparameterize in terms of the total mass, or the precision parameter. So we see the precision is increased by n, our sample size. So we are more confident in our updated mean. And our mean parameter here, well, we can also consider that so the updated mean parameter is just a mixture between our prior guess and our maximum likelihood estimate. And we can show that the predictive distribution, so the probability that our next toss of the dice is equal to j, is just our updated mean parameter there. So again, that's also easy to show. The probability that xn plus 1 is equal to j, given our sample. That's just the probability xn plus 1 is equal to j, given our vector of probabilities, integrated with respect to the posterior. And this is just pj so this is just the expected value of pj given our data, which is pj hat. Okay. The Polya-Ernst scheme describes the distribution of a sequence of random variables, xn, taking values in 1 to k. So we consider an urn with alpha balls, and it has proportion p0j balls of color j for j equal 1 to k. So that means we have alpha times p0j balls of color j. A ball is drawn from the urn, and it's replaced with another ball of the same color, and we set xn equal to j if the nth ball drawn was of color j. So let's draw a picture to understand that a bit better. Okay, so suppose k is just equal to 2. We only have 2 balls. So let's say we start off with 2 black balls and 3 white balls. So in this case, alpha is equal to 5. P0, we can consider 1 to be black and 2 to be white. So P0 of 1 is just 2 over 5. P0 of 2 is just 3 over 5. So what we do is we sample a ball from the urn. Say our first draw is black. We put the black ball back in along with another ball of the same color. And we set our first draw equal to black. Now we have alpha plus 1 balls in the urn. So we have 6 balls in our urn. We have 3 black balls and 3 white balls. We draw another ball from the urn, and we put it back in with another ball of the same color. And we set x2 equal to 2. And we keep repeating this. Okay, so the law of this sequence is given by this term here. So the probability that x1 is equal to j, the probability that x1 is equal to j, well, that's just the total number of balls of color j divided by the total number of balls in the urn. The probability that x2 is equal to j, given x1, we can say j2, x1 is equal to j1. This is just equal to the total number of balls in the urn of color j2. So that's alpha p0 j2 plus, we added one more ball of color j2 in this previous step if j2 is equal to j1. So the indicator that j2 is equal to j1 divided by our total number of balls, which is alpha plus 1, because we added another ball at this stage. And we can keep going. So at stage xn plus 1, given x1 is equal to j1, xn is equal to jn, we have that this is equal to the total number of balls in the urn of color j, which again is alpha times p0j. Let's call it, okay, yeah, we can keep it j. And then we need the number of balls that we added, which were of color j. So this is just the sum from I equal 1 to n of the indicator that j is equal to ji. And how many balls do we have in the urn at this stage? Alpha plus n. Okay, so that's the law of this sequence. Okay, exchangeability and De Finetti's theorem. Exchangeability says that if I have a sequence of random variables, so in this case, let's consider that they take values in 1 to k. This sequence of random variables is exchangeable if I take any permutation of the set 1 to n, so pi is any permutation of this set, then the distribution of these vectors satisfies this equality here. So I can permute the order of my random variables and the law stays the same. So I don't actually care that x1 is equal to j1, x2 is equal to j2. I just care that one of my variables is equal to j1, one of my variables is equal to j2, and so on. So De Finetti's theorem says that if a sequence of random variables is exchangeable, or a sequence of random variables taking values in our discrete space is exchangeable if and only if there exists a unique probability measure Q on our simplex such that this holds here. So this says that exchangeability is equivalent to saying that xi given p, our IID, in this case categorical with parameter p, and p has distribution q. So if I believe my data are exchangeable, then I know that this holds. If this holds, then I'm assuming my data are exchangeable. Okay. So we can show that if the distribution of xn is described by the Polya-Ern scheme, then our data is exchangeable. So that's quite easy to show. We can go through the proof real quick. So let's look at this distribution for the Polya-Ern sequence. So we have, it's given by this here. So we have alpha over P0 J1 over alpha, the number of balls of color J1 over the total number of balls, alpha over P0 J2, plus the indicator that J2 is equal to J1 over alpha plus 1, and so on. Then at the end we have alpha P0 Jn plus the sum from I equal 1 to n minus 1 of the indicator that Jn is equal to Ji over alpha plus n minus 1. So this is the distribution of our first n elements from the Polya-Ern scheme. Okay, so let's rewrite this a bit. Look at this denominator here. This is just the falling factorial. So we can say that, just rewriting this denominator term, this is gamma of alpha plus n. Okay, now let's look at the top. So suppose I have nj of so nj is the count of ji equal to j in this sequence here. So we see that the first time that j is drawn from the urn, we will only have alpha of P0 j balls. The second time it's drawn, we'll have alpha of alpha times P0 j. The second time it's drawn, we'll have alpha of P0 j plus 1, and so on until we have alpha, till we take the last draw, then we have nj minus 1. And you can do this for j equal 1 to k. So we can rewrite this numerator here as another falling factorial. So we have the product from j equal 1 to k, gamma of alpha, okay? And this only depends on these counts here. It doesn't depend on the order in which I saw the variables, the order in which I saw these. So it's exchangeable. So from Di Finetti's theorem, we know that this holds here. So we know that this is equal to the integral so that's what Di Finetti's theorem tells us. And this just gives the moments of the Dirichlet distribution. So we know that Q must be the Dirichlet distribution. Okay. Conversely, we know that if xi given p have categorical distribution. So what we just showed is that if xn is a sequence of, the distribution of xn is described by the Polya-Ern scheme, then they're exchangeable, and this Di Finetti measure is the Dirichlet distribution. Conversely, we can show that if xi given p have a categorical distribution, p is Dirichlet. Then the distribution, the predictive distribution or the marginal distribution of our sequence of random variables is the Pauli-Ern scheme. That just follows from the predictive distribution here, so that we have this if and only if statement here. If the distribution of xn is described by the Pauli-Ern scheme, the distribution of xn is described by the Pauli-Ern scheme if and only if this model holds here. Okay, so now let's move on to the Dirichlet process. The Dirichlet process is an extension of the Dirichlet distribution on the space of probability. So the Dirichlet distribution is a distribution on the space of probability measures on our finite space. We can see it as a distribution on the space of probability measures on our finite space. So now we're extending this to a distribution on the set of probability measures on a complete and separable metric space. So let's clarify this idea a bit more. I'll erase this. Okay. So the Dirichlet distribution defines a prior or a distribution on the set of probability measures on space 1 to k. So we really defined it on the vector, the probability mass on each of these points. But since it's finite, we can derive the distribution on any set composed of these elements. So we can see it as a distribution on the set of probability measures. So just to clarify what this space is, this is the space of functions p from the sigma algebra on our space 1 to k. So in this case, it's just the power set, the set of all possible sets, and it maps it to the unit interval. So it takes a set of elements, a subset of this space, and it maps it onto the unit interval, and it must additionally satisfy two other properties. The first is that the measure of the entire space is equal to 1, and it must be countably additive. So if I take any sets in my sigma algebra, any countable number of sets, then the probability of the union is just equal to the sum of the, oh sorry, this is for disjoint sets. Okay, so now we want to extend this, just replacing the set, our finite set, with a general space X. So the Dirichlet process defines a prior on probability measures on a general space, which we'll call script X. So this space, again, it's the set of probability measures. Here we'll take the Borel sigma algebra. So X is a complete and separable metric space, and this is just the sigma algebra generated by all open balls defined by our metric on X. So it maps this to the unit interval, so it takes some set, maps it to the unit interval, and it must satisfy the same two properties. So the measure of the whole set must be 1. Here we just replace this with x. And it must be countably additive. Okay. We need some additional notation. So I'm using this script px to denote this space here, this set of probability measures on x. And we need to define a prior on this space. We need a sigma algebra on this space. So we'll consider the Borel sigma algebra under weak convergence. So weak convergence is a metric we can use in the space of probability measures. And the Borel sigma algebra is the sigma algebra generated by all open balls under this metric. Okay? So now to the definition of the Dirichlet process prior. It has 2 parameters, alpha, which is just a positive scalar, and our base measure, P0, which is just a probability measure on x. We say that P has a Dirichlet process prior. We denote it with these 2 parameters. We denote it with this notation here. If for any finite measurable partition of our space x, the distribution of this vector has a Dirichlet distribution with consistent parameters here. Okay, so this is the definition of the Dirichlet process prior. It has 2 parameters, as I said before, the base measure, which is the prior guess, and the precision parameter. So we still have the variance of the probability measure of any set is given by this here. So we see that alpha, again, controls the variability. So as alpha goes to infinity, we converge to our prior guess. The Dirichlet process prior converges to a point mass at our prior guess. Okay, let's go back to the Dirichlet distribution and look at important property of the Dirichlet distribution, which lets us define this non-parametric prior. So if we consider B1 to Bm to be any finite partition of this of our space 1 to k, we define the probability of Bi to just be the sum of the probability mass of the points which are in Bi. Then from properties of the Dirichlet distribution, we know that the probability of these points is at these sets is also a Dirichlet distribution with parameters appropriately defined. So what this means is that, let's go back. So what we did here was we just defined, as we did for the Gaussian process, we're just defining a collection of marginals. So for the Gaussian process, we defined a collection of marginals, the distribution of the function at endpoints. So here we're just defining the collection of marginals, the distribution of the probability measure at some finite number of sets. And we have that this marginal property holds. So if I consider A1, K, let's say, where these sets is a finer partition of our space X. So it's a finer partition of B1, Bm. So each AI must lie in one of these sets. It's a finer partition. Then if I look at the distribution of P1, B1, Bm, of the probability at these sets, this is equal in distribution to the sum over I such that AI is in B1, P of AI, sum over I such that AI is in Bn, P of AI. So these two are equal in distribution because of this marginalization property here. So we have that the Dirichlet distribution marginalizes appropriately, and we can show that process exists with these marginals. So the proof of existence, I'm not going to present that. You could simply just apply the Kolmogorov extension theorem. However, the Kolmogorov extension theorem would say that there exists a process on this space without these two conditions here. So just on functions which go from, take sets and map it into the 0-1 interval. So we can't, and so we could restrict our prior to the desirable set that we want here. So we want our functions also to satisfy these two properties. However, this is not a measurable subset of this space without these two conditions, so we can't simply apply Kolmogorov extension theorem, so the proof is a bit more involved. I can give you the appropriate reference if you're interested in seeing the proof, though. Okay. So now let's go to the stick breaking construction. So if P has a Dirichlet process prior with parameters alpha and P0, then it is characterized by this stick breaking construction here. So it's, we have point masses at some parameters theta j, which are sampled from our base measure, and these have weights defined here. Okay. Okay, so consider we have a stick of length 1. So this is why this is called the stick breaking construction. We have a stick of length 1. At the first step, we take V1, which is a beta random variable with parameters 1 alpha. So this tells us the proportion of the stick that I break off at time 1. So at time 1, I break off this proportion of the stick, and I set P1, I'll write it over here, P1 equal to V1. Now, I have this much of the stick left over. It has length 1 minus V1. At step 2, I break off another piece of this stick. The proportion that I break off is V2, which is another beta random variable, independent. So I break off another piece, and the length of this stick is the proportion that I break off times the length of the total stick. So P2 is equal to V2 times 1 minus V1. So now I have a stick of length 1 minus V2 times 1 minus V1 left. And I repeat this procedure again. I take another proportion of the stick, which is V3. So this length of this piece now is V3, 1 minus V1, 1 minus V2. And I keep repeating this procedure. Okay, so this is the stick breaking construction of the Dirichlet process prior. So notice that this means that a sample from the Dirichlet process prior will be discrete with probability 1. Yep, okay. So here's some samples from a Dirichlet process prior. I used this stick breaking representation to sample from the Dirichlet process prior. So I kept sampling these VJs and computing the P's until so you'll notice that the weights tend to decrease. So the proportion of the stick remaining gets smaller and smaller and smaller. So I kept sampling until my computer told me that what I had left was basically 0. So the computer couldn't detect anymore the leftover mass. Okay, so here are some random draws with different values of alpha. My base measure, I just set it to be a standard normal. So here I took a quite small mass parameter equal to 0.01, and you can see that I basically get all my mass at 1 point. So this proportion of the stick, if alpha is large, this is beta. So this is beta 1 alpha. If alpha is large, this will be large, and the proportion of the stick I break off will be quite large. Instead, as alpha gets larger, we see that we have more and more samples with smaller mass. And as alpha goes to infinity, we converge to our prior our base measure.
If you do this, you can do it infinitely. Like, you can always theoretically break, and you will never get to 0, right?
Yeah, theoretically you'll never get to 0. In practice, it's so small that your computer tells you it's 0. Yeah, so here I have, let's see, for this one, I guess I only have 1, 2, 3, 4, 5, 6 points. So already at 6 points, he said what was left over is very, very small. So in theory, I should have an infinite number of mass points plotted here. But the mass is just so small that my...
But would it be when the base measure is Gaussian, if it's uncountably infinite, and you will have countably infinite samples, or also uncountably infinite? What will your draw be?
No, this is the... So I will always have a countable number, infinitely countable number of point masses at some parameters which are sampled from my base measure. That's a characterization of the Dirichlet process. You're welcome. Okay. So if my model is that xi given p, or IID p, and I put a Dirichlet process prior on p, then I have a Dirichlet process posterior with updated parameters. So the Dirichlet process is the conjugate prior. My updated parameters are, again, I increase my precision parameter by n. So I'm more confident now in my mean parameter here, which again, we can just write this as a mixture of my prior guess and the empirical distribution function, or empirical probability measure. Okay, and the predictive distribution is just p hat of b. So the predictive distribution, again, it's just the mixture of our prior guess and the empirical. Okay, now let's introduce the Blackwell and McQueen Ern scheme. Okay, so I think I will go straight to the picture to explain this. Okay. So we start off with an urn with alpha black balls. So the black balls are special balls. Okay. So at step 1, I draw a ball from the urn. I only have black balls in my urn, so I have to draw a black ball. So once I draw the black ball, it reveals its color to me. It has some color, which is drawn from my base measure, so say it's stripes. So I put the striped ball back in the urn with another, and I put another black ball in the urn, so I still have 5 black balls. And then I set x1 equal to theta 1 star. Now at the next step, I have 5 black balls still, but now I have 1 striped ball. So I can draw another ball from the urn. So let's say this time that I draw the striped ball. So I draw the striped ball. If I draw the striped ball, I put it back in with another striped ball. And I set x2 equal to theta 1 star, which is the color of, it's equal to stripes in this case. Okay, at the next step, let's say I draw a black ball. So I draw a black ball, and it tells me my color, theta 2 star. So it's dots. And I put the black ball back in, and I put a ball with dots in. So x3 is equal to theta 2 star. And you keep repeating this, this process. So just at Kn, this will be the, this will be at stage n, this is the, let's see, did I say? Kn is the number of the number of color balls I have. So at this stage, at stage 3, I have Kn is equal to 2. Kn denotes the number of black balls drawn among the first n draws. So formally, the law of this sequence is given by this formula here. So it's very similar to the Polya urn scheme. The probability that the color of x is in some set B is just equal to the, well, at stage 1, I have to draw a black ball. And the probability that my realized color is in the set B is just the prior, our base measure, the mass it assigns to that set of colors. At stage n, I now have alpha plus n balls in my urn. And the probability that my next sample is in the set B is just, well, if I draw a black ball, again, my realized color will be in the set B with with our base measure, the mass of the base measure at B. Or if any of my colors that I put back into the urn are in the set B. So that's the number of previous samples where the samples are in some set B. Okay, so this is the general statement for exchangeability on a general space. It's very similar. So now this is saying that the sequence of random variables is exchangeable if I take any permutation of the random variables, the law is the same. So I don't care whether x1 is in B1, I just care that one of my random variables is in B1, one of my random variables is in B2, and so on. So again, we have this sequence of random variables is exchangeable if and only if there exists a unique probability measure Q. Now Q is a probability measure on the set of all probability measures on our space X. And where this holds here. So this says, again, exchangeability is equivalent to saying that xi given p are IID with probability measure p, and p has some distribution q. So these two things are equivalent. So if I use this model, I'm saying that my data are exchangeable. If my data are exchangeable, then if I believe my data are exchangeable, then this is the model of my data. Okay. So Blackwell and McQueen in 1973 showed that if the distribution of xn is described by the Blackwell and McQueen Ern scheme, then the Di-Finetti measure is the Dirichlet process. And this is an if and only if. So if you want to see the proof of this, you can check out their paper. I think it's only 3 pages long. But I won't be going through the proof here. Okay. So the clustering given by the Dirichlet process. So since P is discrete, almost surely, there's a positive probability of ties among our sample. So we have clustering of our samples. So we can let Kn denote the number of unique values in our sample. Theta star Kn is the unique values. Nj is the cluster sizes. So it's the number of samples equal to the jth unique value. Assuming that our base measure is non-atomic, that means it doesn't have a point mass at any x in our space script x. Then from the Polya-Ern scheme, we can rewrite the Polya-Ern scheme in this setting here. So this just says my first sample is the unique value. Given my samples x1 to xn, the next value, it's either going to be a new value sampled from the base measure with probability alpha over alpha plus n, or it's going to be one of my previously observed unique values with probability nj over alpha plus n. And my unique values are just sampled from the base measure. So our sample, x1 to xn, it can be reparameterized in terms of the unique values, these unique values, and the random partition. So this are the labels which tell me which cluster each subject is in. So Si is equal to j if the ith subject is in the jth cluster. So if I know the partition and I know the unique values, I know the values of x, right? And conversely, if I know x, I know the unique values and I know the labels of each subject. So if I just look at the predictive distribution of these labels, this is known as the Chinese restaurant process. So let's just say what the Chinese restaurant process is. So the Chinese restaurant process, so say S1 Sn is equal to 1, 2, 1, 1, 3, 2, say. So we have 6 subjects. Chinese restaurant process says, so this is table 1. The first customer comes in. So it's S1. He comes in, and he sits at the first table here. So S1 sits at the first table. The second customer comes in. So now S2 comes in. And he'll either sit at the first table with probability proportional to 1, the number of subjects sitting at that table. So that's just 1 in this case. Or he sits at a new table with probability proportional to alpha. So here, at this stage, we have 1 person at this table. So he'll sit at this table with probability n1, or just 1 over alpha plus 1. He'll sit at the new table with probability alpha over alpha plus 1. So he decides to sit at the new table. So S2 is here. Now we have our third subject comes in. So now let's update these probabilities. We have 1 person at table 1, 1 person at table 2, and we possibly have a new table, table 3. So now the probability he sits at this table is proportional to 1. The probability that he sits at this table is proportional to 1. We have to renormalize appropriately. So that's 2. This is alpha over alpha plus 2. And he says, I want to sit at this table. Oops, that's S3. Okay, and then the next subject comes in. He decides to sit at this table. The probability that he sits at each of these tables, we can update it. So before there was 2 subjects, now at this table, oops, that was 1. And we can update our probabilities appropriately. Okay, so we can keep going. The 5th subject, he decides to sit at table 3. This is with probability proportional to alpha. He would have sat at this table with probability proportional to 1. He would have sat at this table with probability proportional to 3, the number of subjects there. And finally, we have the last subject, which sits at this table. Okay, so that's the Chinese restaurant process. So now if we color these tables with colors sampled from our base measure, so we color this table with theta 1 star sampled from P0. So now this table has color theta 1 star. This color has theta 2 star, which is independently sampled from my base measure. And this table is colored with theta 3 star. Then we have the Dirichlet, the predictive distribution of the Dirichlet process. So if we color the tables of the Chinese restaurant process, we have the predictive distribution of the Dirichlet process. Okay, so the most popular application of Dirichlet processes is to mixture models. So we said that the Dirichlet process is discrete with probability 1. And in many applications, we don't want a discrete probability measure. So one way to overcome this is to convolute the Dirichlet process with a continuous, so some parametric density. Then we get a probability, we get a prior on the space of densities or probability measures which are continuous almost surely. Okay, so here is the definition of mixture models. We just say that the density of X given P is just a mixture of some parametric densities with parameter theta And P here is the mixing measure over theta. So one example, we could consider a mixture of normals. In that case, theta would be the mean, and or it could be just the mean, then we would call this a location mixture of normals. Or it could be the mean and the variance, then we call this a location scale mixture of normals. So in a Bayesian setting, we need to put a prior on P, and the common choice is the Dirichlet process prior. Since P is discrete with probability 1, we can represent this as an infinitely countable mixture of our parametric kernels.